All right, so today we'll talk about scheduling large-scale evacuations. This is part of the disaster management project at NICTA. It's a project we've started about a year and a half ago. And we started this project because disasters threaten the lives and welfare of entire populations, and there is a lack of decision support system that allow us to plan and respond to a disaster appropriately. So scheduling evacuations is staged into an evacuation planning phase, where we group population into evacuation areas. We select safe zones and locate the shelters where population should go, and we decide of evacuation routes. After evacuation planning, we have what we call evacuation scheduling, which is given evacuation routes, given an evacuation plan, we want to decide of the timing of the evacuation for everybody. Because we don't want everybody to evacuate at the same time, because it could incur some congestion in the network. So we want a very good, very optimized timing. I will start by describing what an evacuation planning problem is, and I will talk about how we model the evacuation scenario. So on the left side, you have the real-world scenario, where the gray square represents one evacuation area, which is like a group of population. The green triangles represent the safe areas, A and B. And then we have the transit nodes, number 1, 2, and 3. And we have routes, like portions of road that connect those nodes. And that are going to be cut over time as a disaster expands over the network. So for example, at 8 a.m. we might have the road on the right hand corner, which might be cut. And then at 9, 11 a.m. and 1 p.m. the other roads are cut, as for example, a flood is expanding, so the roads will be flooded. On the right side, you have the evacuation graph, which is a modeling of this real-world scenario. And for each evacuation node, so the node 0, we have, sorry. All right. So for each evacuation node, we have a demand, which is the number of people to evacuate from that node, and an evacuation deadline. Since the node would be, since for example, if we talk about a flood, the node will be flooded at 1 p.m., so people must be evacuated by that time. For edges connecting the network, we use a directed graph. So we have, for example, between the evacuation node and the transit node, we have directed edge that goes from the evacuation node to the transit nodes. And then between transit nodes, we have also unidirectional edge that goes from 1 to 3, from 3 to 1. And for each of these edge, we have a fixed travel time, a fixed capacity, and we know at what time this edge is closed. And the plan is to find an evacuation route going from each evacuated area to each safe node. Right. In order to schedule the evacuation, we need to modify the graph that I presented earlier, which we call a static graph, to a time-expanding graph, in order to take into account the time nature of an evacuation, which means that we need to decide when each evacuee leaves. So we cannot use a static graph as itself. So the time expanded graph is a modified version of the static graph, where we include a time step, which is in this case 1 hour. And for each time step, we duplicate the nodes and we duplicate the edges in order to be able to record the flow on each evacuation edge at each time. So on this graph, you have, for example, the evacuation node 0, which is duplicated at each time step. And at 9 a.m., so at 9 a.m. we might evacuate 10 people. 10 is the number above the edge connecting node 0 to node 2. And then we might also evacuate 5 people to an over transit node 1. And then at 10 a.m. we might evacuate even more people, the remaining people. So that's how we manage to record the flow at each time step, the flow of evacuated vehicles. Also, we connect all the evacuated nodes to a super source node and all the safe nodes to a super sink node. So we have a different way to schedule the optimization. One obvious optimization model is a maximum flow over time, where the only objective is to try to evacuate as much people as possible. So we have a flow variable on each edge, modeling the flow of vehicles for each edge at each time step. We have, so that's the departing flow from the source node. Then the second equation is the flow conservation in the graph. So for each transit node, the number of vehicles arriving to that node must be the number of vehicles leaving that node. So the flow on each edge should be inferior or equal to the capacity of the edge. So in this model, which is a lower bound on evacuation timing, evacuees flow freely in the graph. So that means that we do not control, we cannot really control the flow in the graph. We just we just ask people to evacuate in practice, but then we cannot retrace the evacuation for each vehicle. We don't know where people go, so it has a very limited practical importance. So what we would like instead is knowing the flow departing for each node and know where this flow goes. So we would like to know the flow for each evacuated node on each edge. And that's the purpose of our multi-commodity model, where what we call a commodity here is actually an evacuated area that we will denote K. And we record, in this model, we record the flow on each edge for each commodity, for each evacuated area. And as for the free flow model, we try to maximize the flow departing from the source node. We try to maximize the flow departing from the source node. We also require to have one single path per commodity in order to make the evacuation easier. So we believe that in practice, it will be very once it would be very hard to have several paths per area, and it might also be a bit weird to have several evacuation routes per area, because it would incur a lot of confusion in driver behavior. So why would I go here if people are leaving through another route? It wouldn't make sense. It just wouldn't make sense for drivers. So it requires one single path per commodity. And we also have, as a free flow model, the flow conservation. So the flow arriving to one node must be equal to the flow departing from this same node. So the flow is inferior to the capacity of edge. So the sum of the flow for all coming from all evacuated areas. Right.
Carolyn,
yeah,
just ask
sorry.
a clarifying question. Both this multi-commodity and the single commodity version, you're solving that over the entire time-expanded network?
Yeah.
Okay.
Yeah. So we have a flow variable for each dynamic edge. So this model would be very good if we were able to solve it in a reasonable amount of time, because then we would have the flow for each commodity going through one evacuation route to a safe node. The problem of this model is, unfortunately, its scalability. Since we have a lot of binary variables controlling the path that each evacuation area should take, it makes it very hard to solve it in a reasonable amount of time. For example, considering one region with only 195 nodes and 458 edges, that we expand over time in a 10-hour horizon with 5-minute time steps, we soon have an explosion of nodes and edges, which doesn't allow to solve the multi-commodity flow just in a reasonable amount of time. In order to tackle this issue, we designed an approach which integrates planning and scheduling. So we integrate the design of evacuation routes, the scheduling of the evacuation through a math heuristic algorithm that I will detail a bit later. And in order to evaluate our approach, we use agent-based traffic simulation in order to validate the results and also get more insights in the progress of evacuation and unexpected bottlenecks. So we use simulation because optimization, as I said before, has a few approximations. Like we used fixed travel time, fixed capacity on edges. So we don't really model congestion. So the optimization approach we designed for evacuation scheduling is the following. And it's an iterative approach. We start by generating initial path and solve the scheduling problem with this initial set of paths. And then we identify critical node C, and I'll talk about what a critical node is exactly, but we identify evacuated critical nodes. And as long as we still have some critical nodes, we had those nodes. So we try to reschedule the evacuation and to generate more paths, and generating more paths until we find a solution we are satisfied with. So this approach is it's iterative and it's split it into a master problem and a sub-problem. The sub-problem is a problem that generates a path, and the master problem is the model that solves the evacuation scheduling. In this model, we have one flow variable per path and per time step, which records how many people live at time t along a path. We still want only one path per evacuated area. So for all the set of paths belonging to one evacuated node, we add the constraint that only one should be selected. We also allow, so dk is a demand for evacuated node k, and we'd like to maximize the number of people that live that area, but it might happen that we are not able to fully evacuate this area. So the flow variable phi k accounts for non-evacuated vehicles. Of course, we have to respect edge capacity. So for all paths that use one edge, so all paths that so all the vehicles that go through an edge, like there shouldn't be more people than. All right. So for all the vehicles going through an edge, there shouldn't be more vehicles than the edge capacity. And then we link the flow variables with the path. So there should be no flow on a path P if this path is not selected. So since our approach is iterative, we add more paths as so after we schedule the evacuation, we identify critical nodes and we add more paths to the problem. So that means that the number of constraints augment over time, since each new path adds a new constraint. All right, so critical nodes. What are critical evacuated nodes? Well, these are the nodes that we call costly in, they are nodes that, for example, depending on the objective, are not evacuated completely for the maximum flow objective. And if we manage to evacuate everybody in the given horizon, there might be nodes that are evacuated too early if our objective is to evacuate as late as possible. Or conversely, if we try to evacuate as soon as possible, these are nodes that are evacuated later than others. So we try to find, we detect these nodes in the solution. For example, this node number B is a critical node. Since, as you can see just above the node, we only have 5 people out of 10 which are evacuated. Whereas for node A, we have 10 people out of 10 evacuated, and for node C, 5 people out of 5. So why is that? We can see that for node A, we have one path that goes to safe node D, and which has a capacity of 20 vehicles. Since there's only a demand of 10 for evacuated node A, and then we can just evacuate everybody. However, for node B and C, we can see that node B and C both evacuate to node E, and the path, their path share one edge, which has a capacity of only 10. So we cannot evacuate everybody in the same time. We have to make decision. So nodes B and C are called conflicting nodes. And the edge is saturated since it's shared by B and C. So our goal is to generate paths that avoid sharing edges. So that's how we generate new paths. So if we generate new paths that avoid sharing edges, it would improve the scheduling of the evacuation because we will be able to evacuate more people in the same time. So our approach is to use cost to incentive path, avoiding the congestion. Just one thing, so the initial set of path we used is just shortest path from one evacuated node to the closest safe nodes. Well, in order to generate more paths, we are going to use an approach which uses the shortest path, but with different cost on edges. And the cost of one edge is computed as follows. So it's an average between the travel time of this edge. So we compare the travel time on one edge which is used in a path to the maximal travel time over all the edges used in path. And if this edge has a very big travel time, that it might not be interesting to use it, and or we would at least try to find another edge for which travel time will be shorter. We also count the number of occurrence of one edge, which means that for in the set of paths, so if we have a set of path omega, we just try to find out how many paths share this edge. And if a lot of paths share this edge, then this edge is also going to be more costly. And finally, we also check what is the capacity used on one edge. So if the capacity is saturated, we also try to avoid using that edge. So for generating new path, we try to minimize so the objective function. So for each evacuated area, we want one path per evacuated area. So that's the unicity and continuity of the path. One objective that we have is trying to postpone the evacuation. Because as a disaster unfolds, more information becomes available on the nature and extent of the disaster. We want, for example, to avoid false alarms because there might be a predicted disaster which will actually not happen, so it's not worth starting to evacuate a urban area where there will actually be no disaster. And postponing the evacuation will also allow extra comfort for evacuees because it will be less time spent in shelters. Some disadvantages of this approach is that as a disaster unfolds, more edges become unavailable. They might be cut by the flood or and also, well, one consequence of less edges available is that it might require to increase travel time or distance for evacuees. In order to postpone the evacuation, we modify the objective of the master problem. And we include a time decreasing cost to this objective. I'm going to present results of our models on a case study, which is the Hawkesbury-Nepean area, which presents a major flooding risk. There is this Warragamba Dam that that is likely to, I don't know, to break or yeah. And this Hawkesbury-Nepean area has about 70,000 residents that we would need to evacuate in a few hours if system breaks. And our objective, as I said, is to evacuate as late as possible. This is the graph representing the Hawkesbury-Nepean area with transit nodes as represented as points, evacuated areas represented as squares, and safe areas represented as green triangles. So the results are as follows. So based on this case study, we create some smaller instances, which are a subset of 2 to 50 evacuated areas, considering that the original one has 50 evacuated areas, and subset of edges. And we also generate other instances of increased population, where the number of evacuees is increased from 10% to 200%. So that will allow us to have more instances, more results to compare. So first, this table compares the free flow models and the multi-commutative flow model and the path generation model. We compare the computational time of all of them, depending on the number of evacuated areas, 2 to 50. So we can see that free flow, the computational time of free flow is very low, about 1 second for all these instances. The multi-commutative flow, however, even for those reduced instances, is not able to compute a solution in less than 30 minutes, as soon as the number of evacuated areas is higher than 8. And finally, our path generation algorithm performs quite well with a solution for all these instances in less than 10 seconds, with an optimal solution.
So can I ask?
Yeah, sure.
It's not monotonic.
Yeah.
That's intriguing.
For the areas, you mean? Like, you mean?
The last column.
Yeah. No, because so we also use some randomized cost for the last model in order to generate more path. So sometimes you have better path than others.
So something else is that the reduced instance of the instance with 20 nodes doesn't necessarily contain the instance with 10 nodes. There are different instances with different road network.
Okay.
So there's just random instances with different sizes that are based on one instance, but they are not.
Oh, the instance is random, or the solution technique involves randomness?
Oh, well, there is some random aspect in the solution technique, but the thing is, when we generate the instances, the smaller one, we just take a random subset of the main instance.
Oh yeah, okay. So it is sort of still a subset, like it's a hierarchy, but they're random.
Yeah, but they're not necessarily related to one another. I mean, as I said, the 20 doesn't contain the 10.
Yeah.
So the 20 may be much harder than the 10, and the 30 is easier than the 20.
Right.
Like if you only have the 30, which are very close to safe areas, and if you have the 10 that are very far away, then the 10 might be harder to evacuate than the 30.
Could you parameterize that somehow? Just Sorry, I should stop interrupting.
No, they
No,
would be
it's
aware,
fine.
but it's just
That's
that it was just to see how far could the multi-commodity flow go.
So this table represents the percentage of evacuees reaching safety over time for the increased population instances, containing a demand increase from 0 to 200%, 0 being the original instance. Again, free flow performs very well. 100% of evacuees reach safety. The multi-commodity flow does not manage to compute a feasible solution in time. And our path generation approach allows to evacuate 100% of evacuees up to a demand of increase by 40%, and still allows to evacuate 87% of evacuees for a demand increase of 200%. Considering, like as I said earlier, free flow is quite difficult to put into practice because we don't know where evacuees go and they use all paths. Whereas the path generation only use one path per evacuated area. So this table represents the time at which the evacuation starts for free flow and path generation, forgetting about multi-commodity flow. And we try to delay the evacuation, so we try to evacuate as late as possible. So for the original instance, free flow it starts evacuating at 8:35, and our path generation at 3:20. So yeah, it's about like 5 hours of difference. Okay, so after the results, I'd like to give a word about the optimality of the approach, since our proposed approach finds solutions when a multi-commodity model cannot, but we cannot really assess how far from the optimal it is because we only generate a subset of paths, and our approach is iterative. So we don't have the complete set of paths, so it's quite hard to evaluate. On the other hand, free flow model seems to provide better results, but as I said, how unrealistic are they? So in order to compare them better, we have two approaches. One of them is to derive an upper bound from free flow, and the other one is to simulate the evacuation. So the upper bound approach is as follows. So we would like the flow of evacuees to generally converge. So what we do is to try for one node, we try to have fewer edges leaving one node than edges arriving to that node. So the thing is, with free flow solutions split the flow of vehicles, and evacuees from the same area follow a different path. We want to avoid that, and to make it as close as possible to path generation solutions, which are generally convergent. So we want to compare free flow and path generation with convergent flows. And this table presents the results of the upper bound we derive for free flow, where we have convergent flows. And we can see that the results between the convergent free flow and the convergent path generation are much closer than the results for the original models. For example, for the original instance, with convergent with free flow, you have an evacuation starting at 3:40, and for convergent path generation, you have the evacuation starting at 3:50. So the conclusion of this is if you use convergent flows, you realize that our path generation model is quite close to an optimal solution. Yes. A few words about simulation. So for simulation, we simulate each vehicle, each evacuee as an agent, and we evaluate different behaviors. These behaviors can be fully compliant with the plan, so we simulate the exact optimization plan that we came up with. We also have other behaviors which alter departure times, which are what happens if evacuees do not evacuate at the time we tell them to evacuate, but decide to evacuate a bit earlier or later. And finally, we have behaviors like random behaviors. So evacuees, some evacuees would follow the plan, but others would evacuate earlier or later, and others would choose a totally different plan, going to a totally different safe area by a different route. The following chart represent the evacuation profiles for free flow and path generation of the optimization approach compared to the results of simulation for different behavior. So the blue curve is the optimal plan, the optimal evacuation plan. And on free flow, it's and then we have the orange curve, which is a plan where people would start to evacuate a bit earlier or later. And finally, the red curve represents the plan where some people would just go to the shortest, will just follow the shortest route to the closest safe area. So for free flow, if people start having random behavior, you can see that the number of vehicles evacuated dramatically drops, and even more if people just go to the closest safe area by the shortest route. Whereas for our path generation models, which start evacuating a bit earlier than free flow with only one path per evacuated area, the model is still quite robust, and we can see that the simulation gives results that are quite close to the optimization model. And even if vehicles just follow the shortest route, we can still evacuate most of evacuees on time. This table represents the percentage of vehicles evacuated for free flow and for the path generation approach. It compares the results of the optimization and simulation. So on average, for all these instances, the simulation is only able to evacuate 66% of evacuees for free flow, compared to optimization, which said we are able to evacuate everybody. And for the path generation approach, the optimization and simulation results are quite close, as shown in the chart before, with 2% of difference on average. Finally, I'd like to question the quality of the plans that we generate with the path generation approach. So the path generation heuristic tries to generate different paths for each evacuated area in order to share as few edges as possible with other evacuated areas. One problem is that the paths that are generated might not be so evacuee friendly. As you can see here, the path used for these evacuated areas it looks like it's not using the shortest route, which is normal. That's what we ask. We ask to generate a different path. But then in practice, would people accept to follow this path if it looks a bit weird? Also, we might realize on this image, evacuees could have gone to a closest safe node than the one which was actually chosen. So why is that? Well, as I said, a heuristic is a combination of three weighted factors. So this is the reason why we have this path which does not use the shortest route. And it's actually something we are working on at the moment in order to try to improve it. Right. So yeah, like we try to improve the newly generated path. Yeah, I think I've said enough about this one. Okay. So yeah, we're still working on this path generation approach in order to generate more evacuee-friendly paths that will still allow to evacuate as much people as possible. Okay, well, thanks for coming. Thanks to all of you for coming and for listening to me. And I'm looking forward to your questions. Thank you.
I'll ask a question.
Mm-hmm.
So back in the convergent flow results,
Yeah,
I
sure.
was curious why the free flow wasn't a lower bound to the path generation.
So the free flow approach is a very much a lower bound, considering that it evacuates everybody through all paths. But it's not precise enough. I mean, it's too unrealistic, too optimistic. The path generation just uses one path per evacuated area, and that's what we want. But we are not able to use a multi-commodity flow to compute that solution because the model is just too big. So yeah, we try to derive this convergent free flow to be as close as possible to one path per evacuated area. I don't know if I answered your question clearly.
I think what Kelton was asking is, you mean in the results?
Yeah, so in convergent, 20%, 5 hours for free flow, 3 hours for path generation.
So the thing here that may not be clear is that in that case, we're trying to push the evacuation as high as possible. So it will be an upper bound, not a lower bound. And it's more or less an upper bound. So for us, if we evacuate at 5 hours, it's better than evacuating at 3 hours because it gives us 2 hours to warn people.
Yeah. Okay.
But if you look at the results at the bottom of the table, you'll see that, for instance, for 70%, free flow is 1 hour 15 and path generation is 1 hour 20. So it means that path generation is a bit better. But what doesn't show here is that this model doesn't finish in 2 hours. So it's not the optimal solution. We are at 10%, I think.
Great.
Can you go 2 tables back? Can you go 2 tables back?
Yeah, sure.
So I don't know how many slides that is. Back.
This one?
Yep, exactly. So wouldn't this sort of indicate that the constraint you're giving to the path generation, that you can only follow one path that is a bit of a restrictive constraint, given that you may not evacuate all people, whereas in other, I mean, more freely approaches, you could evacuate potentially all people.
Sure. The thing is, evacuate, like at some stage, we need people to control the evacuation. And if we use several paths per evacuated area, it becomes very uncontrollable. Plus, I think I've stated that earlier as well, but if you use several routes, then people might get confused and see other vehicles using a different route, and then they will be, why am I using this route? Am I going in the other direction? Am I going in the wrong direction? So I don't know what exactly was your question about it, if it's restrictive.
So if you've got Menke's approach, how much does your approach slow it down by just taking the one path?
Sorry, say again?
Does it slow it down, taking the one path, just having shortest path only? Does that slow it down from Menke's potential approach? The evacuation.
Sure. Did you get his question?
No.
Can you reformulate your question?
Yeah, so Menke's gave it, you said you take the shortest path, and
Yes.
you just choose that path. Is that correct?
That's how we generate the initial path, but then we generate more paths, which might not be the shortest ones.
No, if you
or the
generate
quickest.
multiple initial paths, as Menke suggested, is that potentially faster, or does that not help?
If we generate more paths that are not the shortest path, is it faster? Is that your question?
Yes.
Yes. I don't have a table comparing the results now, but yes, it is faster.
Okay, thank you.
Can you give some intuition as to why the free flow with convergent paths is not a reasonable solution? Like why is it?
Why don't we use it?
Why is it an unreasonable solution? I mean, the motivation before was if you're at a node and people are going different directions, you don't know who's going where. But if it's convergent, everything sort of comes and there's only one exit.
Yeah, but it's still not one path per evacuated area, and it's still quite untractable.
I think the problem is it means that the person in charge of the equation will just tell people leave your house, and there will be someone on the way who will tell you which direction to go. So as an evacuee, you don't know anything. You just know I need to go out, and then someone's going to tell me to go right, and someone is going to tell me to go left. And so that the goal that what we want to be able to do here is to send a message to the evacuee saying, take the M1, then the M3.
If there's only ever one outgoing edge, isn't there only one path I could possibly take in the free flow convergent model? Maybe I'm misunderstanding.
Yes, there is only one path in the solution, but in the implementation of the solution, it means that you need, in the way you communicate that to the evacuees, you could potentially, you could actually, you're right, you could actually rebuild.
Because if it convergent just means you only have one outgoing edge, you should be able for any source node to be able to say what the one path is. It can't have more than one path because it only has one outgoing edge.
I think when we do convergent, we say if we have two incoming edge, do we have two outcoming or just one outcoming? One outcoming. Possibly.
And so, I mean, you mentioned taking other paths as your initial seed set for the path generation. Have you considered taking paths from free flow, or taking information from free flow to inform the path generation?
We haven't done that. No.
So in your objective function, you're maximizing people that leave the dangerous and the affected areas, right? Does it change anything if you change that to people actually arriving at, say, target sites? It should be the two, so they should be equal, right?
Yeah, it's equivalent to saying we maximize the flow arriving at the safe ones.
But does it have any impact on how calculation is carried out?
Not that I noticed. I think we've tried with both approaches, and it was not similar. Any other questions over there?
No more questions? Well, thanks again, Kari. Thank you, remote people. Have a good day.
Thanks, Victor.
Thank you. Bye-bye. Thanks for your remote control.